What is this molecule? As you work your way through organic chemistry, especially the unit on spectroscopy, you're going to come across a couple of words that are often used interchangeably: degrees of unsaturation, units of unsaturation, and index of hydrogen deficiency. I certainly use all of those words interchangeably, and they all mean essentially the same thing. They all refer to the extent that a hydrocarbon is unsaturated. Well, okay, so what does that mean? How do we know what a degree of unsaturation is, and how do we determine how many degrees of unsaturation a molecule has? To do that, let's do a thought experiment. Imagine I have a 5-carbon chain. How many possible hydrogens can we put around this carbon chain? What is the maximum number of hydrogens that 5 carbons can hold? Well, there's a formula for that. Do you remember the formula for the maximum number of hydrogens that a given number of carbons can hold? The formula for the theoretical maximum number of hydrogens for a given number of carbons is 2n plus 2, where n is the number of carbons. So for 5 carbons, 2 times 5 is 10, plus 2 is 12. For 5 carbons, the theoretical maximum number of hydrogens would be 12. But how does that formula work? Why is it 2n plus 2? It's not good enough to just memorize formulas. It's important to understand why the formula works so that when you see novel situations, you know what to do. So where do we get 2n plus 2 from? If we have 5 carbons, each carbon can host 2 hydrogens, one above and one below. This gives us the 2n number of hydrogens. And notice that the 2 end cap carbons each have one valence open that can host 2 more carbons. That's our plus 2. So here's our 2n plus 2. This is why the theoretical maximum number of hydrogens for a given number of carbons is always 2n plus 2. Now, not all molecules will have its full complement of 2n plus 2 hydrogens, and one of the reasons might be unsaturation. Let's take a look at that now. Let's do a thought experiment. Let's say I want to put a double bond between carbon 1 and carbon 2, an alkene. Now, I'm not suggesting an actual reaction to do this. There aren't really any reagents that do this in any kind of specific or predictable way, but just as a thought experiment, if I wanted to put an alkene between carbon 1 and carbon 2, I could not just add in a pi bond. Carbon already makes 4 bonds. In order to add in a pi bond, I would have to take away some hydrogens to leave up enough valences to put a pi bond between carbons 1 and carbon 2. Now, what would that look like? If I continue with this thought experiment, I would still have the complement of 5 carbons in a chain, and now I want to add a pi bond between carbon 1 and carbon 2. How would that change the structure? I would still have most of the hydrogens in place. I would still have hydrogens on each of these carbon atoms, and my end cap carbons would still have their hydrogens. But notice that I am 2 hydrogens short. To make room for the pi bond, I had to take away 2 hydrogens, so now I am 2 hydrogens deficient from what I should be given my 2n plus 2 formula. When the hydrocarbon did have its full complement of hydrogens, the full 2n plus 2, we call this type of molecule saturated. When a molecule does not have its full complement of hydrogens, we call this type of molecule unsaturated. So to get this unsaturation, I had to remove 2 of these hydrogens. And this is an important feature of unsaturation. For every 2 hydrogens removed, that equals 1 unit of unsaturation in the molecule. And that leads us to our first principle of units of unsaturation. Every pi bond in a molecule is 1 unit of unsaturation. The presence of any pi bond means we had to get rid of 2 hydrogens, means we have 1 unit of unsaturation. Any pi bond is a unit of unsaturation. And that pi bond could take any form. This one is an alkene, but it could also be the pi bond of a CO double bond, a carbonyl. Could be a pi bond within a benzene ring. Could even be a triple bond. And that's an interesting case because a triple bond has 2 pi bonds in that functional group. So a triple bond would be 2 units of unsaturation. To put a triple bond here, I would have to get rid of these 2 hydrogens as well, adding to a second degree of unsaturation. Let's continue the thought experiment, and instead of trying to add a pi bond to this molecule, what if we tried to make this molecule a ring? What if we tried to connect this carbon on the left with this carbon on the right to make a 5-carbon ring? Again, we can't do that because all the carbons already have all of their 4 bonds. In order to do that, we would have to get rid of the hydrogens on the end cap carbons to open up a valence on either side so we could wrap it around and form a ring. We would then have the 5 carbons present in a cyclic ring with single bonds connecting them all. Each carbon then would still have the 2 original hydrogens attached to each carbon. So we still have 2n hydrogens, but we don't have the plus 2 anymore. We are now 2 hydrogens short. This means we now have another unit of unsaturation. Anytime we have a ring in a molecule, that's another unit of unsaturation. So these 2 principles, any pi bond and any ring, all add a unit of unsaturation to the molecule. Anytime I have a pi bond, anytime I have a ring, I'm going to add an additional unit of unsaturation to the molecule. Because when I want to make that pi bond, when I want to close the molecule into a ring, I have to remove 2 hydrogens to open up valences to accommodate that transformation. The removal of any 2 hydrogens is a unit of unsaturation. With that understanding of units of unsaturation in mind, we can look at any structure and very quickly figure out what is exactly the degree of unsaturation for this molecule. All we have to do is count up every pi bond and every ring in that structure, and we have our answer. If you look at isoamyl acetate, the primary flavor component of banana flavoring, all I see is the one carbon-oxygen pi bond in this molecule. So isoamyl acetate has a degree of unsaturation of 1, just the one pi bond. If I look at glucose, the primary energy source for our bodies, all I see in this molecule is one ring. So glucose also has an index of hydrogen deficiency of just one for the ring in glucose. If I look at the structure of sucralose, a chlorinated molecule that is the artificial sweetener Splenda, I see that it has one ring on one side and one ring on the other side and no other pi bonds. So this has an index of hydrogen deficiency of 2 for Splenda. Looking at the structure of aspartame, which is the artificial sweetener NutraSweet, I see that it has a couple of carbonyls. A carbonyl here, here, and here. That is 3 carbonyls. That's 3 pi bonds in the molecule. So already that's 3 units of unsaturation. And I see it has the benzene ring. Now, I want you to pay attention to the benzene ring. It has 3 double bonds in the structure and 1 ring. Every benzene ring accounts for 4 units of unsaturation, 3 from the pi bonds and 1 from the ring. So every time you see a benzene ring, you automatically know it's going to have 4 units of unsaturation. So combine that with the 3 units of unsaturation from the CO double bonds, and we see that aspartame has 7 units of unsaturation in this molecule. What is this molecule? This is steviol, one of the components of stevia, the artificial sweetener. And I look at this, all I have to do is count up the pi bonds and the rings to figure out its degrees of unsaturation. I see the carbonyl in the bottom left, that's 1 degree of unsaturation. And I look at the ring structure, it's got 1, 2, 3, 4 rings in the molecule. Yeah, this one over here is a little bit weird, but it's just 2 rings right next to each other. So 4 total rings, plus an alkene in the top right. So the 2 pi bonds and the 4 rings make a total of 6 units of unsaturation for steviol. This structure is cinnamaldehyde. The cinnamaldehyde is the primary flavor component of vanillin. I'm just kidding. It's the primary flavor component of cinnamon. I see the benzene ring. We talked earlier. The benzene ring is 4 units of unsaturation all by itself. An alkene makes 5, and the carbonyl makes 6. This molecule has 6 units of unsaturation. For these 2 structures, go ahead and pause the video for a minute. See if you can figure out the units of unsaturation for these molecules. For amygdalin A glycan, it's the primary toxic component of peach pits, which is why you should not eat peach pits. I see the benzene ring, again, that's 4 right away. And the carbon-nitrogen triple bond, how do we handle that? The nitrogen-carbon triple bond has a sigma bond and 2 pi bonds. So a triple bond accounts for 2 units of unsaturation. Combined with the 4 units of unsaturation from the benzene ring means amygdalin A glycan has 6 units of unsaturation. Capsaicin, which is the primary component of chili peppers, has 6 units of unsaturation as well. It's got the benzene ring for 4, the carbonyl for 5, and the alkene for 6, giving capsaicin a grand total of 6 units of unsaturation. This is how we can look at any structure and determine its degree of unsaturation. What's going to be a little challenging, a higher ninja level, is if you're not given the structure and you're only given the molecular formula. How do you take just a molecular formula and figure out how many units of unsaturation a molecular formula has if you don't know what the structure is? That's a very good question, and I have a simple formula that you can use to figure out the degrees of unsaturation just from the molecular formula, and I'll post a link to that video down below. With these simple rules, you can look at any structure and quickly and accurately determine the degrees of unsaturation for that molecule.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.